Welcome to lesson 2. This is about heterogeneity and in particular about unobserved heterogeneity. So the idea is how to discover if there is an observed heterogeneity, and then later we'll see how to deal with it. I am Teodosio Pérez Amaral, and I will be your teacher for this lesson 2 again. The introduction is going to tell you what is the framework in which we are going to work with. We have YIT, which is a scalar. It is the dependent variable, and then we have a set of explanatory variables, capital X, that has a subindex k, because k is the order of each of the explanatory variables in the set. KIT is the three subindexes that you will probably have not seen before, and if you have seen them before, maybe this is not the course you would like to be enrolled in. T equals 1 to capital T time, I equals 1 to capital N individuals, and K equal 1 to capital K explanatory variables. Usually the models that we are going to deal with are linear in the parameters, and the reason is that they are easy to interpret, easy to estimate, and they take a little time in computation. So, and they are considered like a first approximation to an unknown relationship, and they are typically useful in economics. The linear models are common for measuring effects of both qualitative and quantitative factors. Typically, quantitative factors are numerically expressed quantities, and qualitative are expressed in terms of words, and the idea is that they represent different categories. So in the class, if you have a set of people, some are males, some are females, that is qualitative. Some people are tall, some people are short. If you leave it like this would be qualitative also. Some people have black hair, some people have white hair or yellow hair. Those are qualitative data. In this particular case, we are going to deal with an example in which we are going to work through what is the way of discovering unobserved heterogeneity, and we are going to see how this can be done easily, and that Stata does a lot of this for you automatically, except that you have to understand what is the output. If you don't understand the output, Stata will not help you very much at all. Here we have a model, upper model, in which we have YIT equals alpha star IT plus beta prime IT XIT plus UIT. You see here that you have subindexes IT for alpha and beta. What does that allow? That allows for a lot of heterogeneity. That allows for too much heterogeneity. So this model, which is different for each individual and time period, will be very general but very useless. It will not help very much in the modeling. You are not going to learn very much about the alphas and the betas because all of them are different. Again, you are interested in alphas and betas. That's all we care. If we knew alphas and betas, we would stop the class and go drinking beer, because that would be all we care about. But we don't know what are the values of alpha and beta. We have to guess, and the guessing is called estimation. Let's see how you have different treatments of the unobserved heterogeneity. You can use a model for each individual in which you have a sub I in alpha and beta, and this model, you know, it may be useful or not in particular cases, but in general, if all the individuals behave differently, we are not going to be able to learn very much at all from such a model. Restrictions are very important. Why are we talking about restrictions? Because most of the problems and most of the efforts of an econometrician are devoted to find restrictions and apply them. If you have a lot of restrictions, that is very good, because in that case you're going to be able to estimate with precision. If you don't have restrictions and you have a very large and general model, then you don't learn very much from the model or the estimation. So we want to have as many restrictions as possible whenever those restrictions are not rejected by the data. So we would like restrictions that are correct, and we just cannot deal with restrictions that are incorrect. If the restrictions are incorrect, your estimation is going to be biased and inconsistent. So restrictions are important. Let's try to impose as many restrictions as we can, but with common sense. This first model that you have in the top, at the bottom of this slide, you see it's YIT equals alpha star I plus beta prime XIT plus UIT. This is common slopes and different constants. This is the model that we have called before the fixed effect model. It is one of the most typical models that we are going to deal with. Sometimes we put others, but this is the most important basic model, and this is telling us that we are going to use different constants but the same slope. So it is like the first graph that we saw in the previous lesson 1. Would be to compare the models and to use them in an appropriate way. As we see here, it says that in general, case 2 has little interest, and the interest centers on cases in which you have like S1, the sum square residuals of the first unrestricted model, S2, which is the model corrected by individual means, S2, and then the pool model, which is S3, that corresponds to a situation in which this is the most restrictive model. There is a chain of inequalities, and S1 is smaller than S2 is smaller than S3, telling us that the more restricted model has a larger sum square residuals and therefore a fit that is more poor than the fit of the other less restricted models. So this is a typical situation, and we would like to build on that in the next few transparencies. In this transparency 7, we see that we have a set of restrictions, and the restrictions are very important because they are going to help us estimate more efficiently. And the idea is, for instance, up there you have all betas are equal to each other, and that means that the alphas may not be. The next model, H3, that tells us that is the pool model that is going to tell us that everything is the same for everybody, all the alphas are the same, all the betas are the same, and it is the pool model which makes this many k plus 1 times a minus 1 linear restrictions. You see, now we are going to work with the F-test and the nested hypothesis. So we're going to check whether a model that is a special case of another one is really fitting the data well enough. There are several different comparisons that we can do. Here we have one of them, which is a pool model against the unrestricted model. This is something that you can do, but it is not something that you do that often. So that's why we will jump to other cases that are more common, not necessarily more interesting, but more common. And in this case, we are going to center our efforts on this particular case in page 9, fixed effects, common slopes and different constants against the unrestricted model. That would be one of the possibilities, one possibility that is entertained in many cases, but this possibility is something that in this particular course I'm not going to go in detail, because there are some others that are more interested than this one, more interesting than this one. The test of H4, which is page 10, is more interesting than the previous one. No, it's more interesting, it's more common than the previous one. It is telling us how to compare two different models that had some square residuals of S3, which is the pool model, and then the other model that has some square residuals S2, which is the fixed effect model. So this is the typical situation, a situation which is routinely done by Stata. The output of this test is always in the lower bottom part of the Stata output. A lot of people don't care about it or don't see it, but it's always there. What is telling us is, the idea is, can we use the pool model, which is very efficient but very restrictive, or should we use the fixed effect model, which is less efficient but more restrictive? But it is less efficient and less restrictive. So pool, most efficient, most restricted. Fixed, it's a little less efficient and less restrictive. The F-test that we are going to deal with here is very typical, and the idea is as follows. We are trying to compare the pool model and the fixed effect model. What would happen if the two are more or less the same? If the two are more or less the same, the sum square residuals S3 and S2 would be close. And then S3 minus S2 would be small. But how do you know what is small and what is not small? Well, you divide, you take the mean, divide, you use an average over n minus 1. N minus 1 is the number of restrictions that convert the pool model, convert the fixed effect model into the pool model, n minus 1, because it collapses all the alphas of the fixed effect model into 1, which is the only alpha in the pool model, and that would be the numerator of the F. The denominator of the F would be S2 over this quantity. This quantity is NT, which is the sample size, minus N, which is the number of constant that the fixed effect model is using, and then minus capital K, which is the number of slopes that the fixed effect model is using. So that would be the interpretation of this formula. So if you read it in a more abstract way, that would be the difference in sum of square residuals, S3 minus S2, averaged by the number of restriction, is compared with the sum square residuals normalized by the number of degrees of freedom. So we have a numerator that has an n minus 1 there, which is the number of degrees of freedom of the numerator, and that is the number of restrictions that we are testing, and a denominator which is the S2 over n times t minus 1 minus k, capital K, and that would be the proportional to the variance of the unrestricted model. So we have an expression that can be read in different ways, and that will be again read in a slightly different way. That will be the difference in sum square residuals, average difference of sum square residuals, divided by the variance of the unrestricted model. That would be the interpretation of this f and all the f's that you have seen previously. So that is the way to read the f. You have n minus 1 degrees of freedom in the numerator because that is the number of restrictions, and you have n open parenthesis capital T minus 1 close parenthesis minus capital K degrees of freedom in the denominator, because that is the difference between the sample size and the number of parameters being estimated. Now the idea is, if the test does not reject, you can use the pool model. Typically the test is rejected and you cannot use the pool model, and you have to use a model that allows for different constants. That is the typical case. Knowing what is big and what is small depends on the critical values of the f. The critical values of the f, typically for this type of situation, is around 2 or a little higher than 2, so that you need to look at the tables if you want to be sure. Of course, Stata prints for you the p-value, and the p-value is going to tell you what is the probability of obtaining a value bigger than that one that you have obtained just by chance. P-value means if you have a p-value that is smaller than 0.01, then you would reject the null, and if you reject the null, you would have to use an estimator or a model that allows for different individual effects. There are other ways of dealing with this. We just stick to the f-tests which are available in Stata and in other packages. And to conclude, I would like you to think of these conclusions and suggestions. First, the f-test can be used sequentially, so that you can go from one general model to a nested model and continue like this, nesting hypothesis, and you can perform the test in order because they can depend on the decision that you took before. And there may be some contradiction, but typically the contradictions are due to the data, and they are typically the contradictions that you find in common life, nothing particularly striking. And you see also that many tests are printed by default in the statistical packages. You just have to look at them and understand. You have to understand the degrees of freedom. If you don't understand the number of degrees of freedom, then you're lost because you don't know what you're testing, and that is really problematic. Other tests can be computed easily using some square residuals, and change of structure can be computed and tested across time and across groups, and that is something that may be useful in some cases, that is easy to do, and that will help improve a lot your final project. F-tests are easy to formulate and compute and interpret. They are flexible and useful for panel data. There are other tests such as Huffman type test and likelihood ratio and Lagrange multiplier test that may also be very useful, but we are not going to go through that in detail because those really belong to an advanced econometric course, and this is a panel data course.